Okay, welcome to this week's ICTS String Seminar. We are very happy to have Manuel Loparco with us today. He's going to tell us about physical insights from the Hilbert space of QFT and de Sitter. Please.
Thank you. And thank you, Surat, for allowing me to present my work here and for everyone of the people that are here. Yeah, so I'm a PhD student of João Penedones at EPFL, and I'm very happy to tell you about what I did during my PhD. And so the idea is to study quantum field theory in cosmology or in de Sitter, and what are the reasons? The first one is we want to really understand the quantum origin of our universe. We need to start from somewhere, and we think a good first step is to at least understand the basics of QFT in de Sitter first, which you might be surprised, but there's a lot of things that are still controversial. But why is that interesting is because even just QFT in de Sitter already accounts for the origin of structure in our universe. The story is that these quantum fluctuations then got stretched to super horizon scales and then formed all the structure we observe, such as galaxies, etc. So the observables that one computes in QFT in de Sitter are related to observables that people actually detect in the CMB or large-scale structure. And if you are more formally inclined, then there's other reasons, such as the fact that it's a nice playground to understand how QFT works once the background is time-dependent. And another perspective is also that if you think of Euclidean de Sitter, then that's just a sphere. And the fact of having a maximally symmetric space with one tunable parameter, one tunable scale, allows you to say new things about RG flows. And that's interesting in its own right. So the goal is to understand the foundations of QFT in de Sitter. And group theory will be the key to do this through this basic principle, which is that a Hilbert space of a quantum field theory on any manifold can be decomposed into a direct sum of Hilbert spaces associated to the unitary irreps of the isometry group of that manifold. And from this very simple principle, there's a lot of physics that can be learned. And with this in mind, the mission is then to try to put QFT in de Sitter on the same footing as QFT in flat space, that we really understand beyond just perturbation theory. So here's an outline. And there are three natural ends to this talk. So if we don't get there, it's okay. It's more important that you guys ask actually questions and everything is clear. I will first review a little bit the group theory of de Sitter, and I will say how that can be used to derive a spectral decomposition for correlation functions. And then the meat of what I want to talk about is what physics can we learn from this spectral decomposition. And so one thing I will talk about, a paper I put out this year on RG flows in 2 dimensions. And then I will talk about some work in progress related to what does it mean, what is really a photon in de Sitter space, and then about decays and particle production. And this is all related to this group theory story and the spectral decomposition. Okay, so let me start from the group theory. A nice way to see de Sitter is to embed it in a higher dimensional Minkowski space. And then you can embed it as some hyperboloid with a characteristic length scale R, which is related to the Hubble constant. They're just one is the inverse of the other. And if you think of correlation functions that depend on 2 points, 2-point functions, then you can build a natural invariant out of 2 points with the inner product in this embedding space. And so any scalar observable, if it's de Sitter invariant, then it must depend on this combination. And if you're familiar with the flat slicing coordinates, then this is how it looks like, but that's not important. Then it will also be useful to think of tensor fields embedded in this higher dimensional Minkowski space. And so when I use these capital letters for the indices, I mean that this tensor is in the embedding, and then you can recover the local coordinates version with the pullback. Okay, so this is just the setup notation. And the form of this embedding makes it manifest that the isometry group is SOD plus 1,1, which are the pseudo rotations on the surface of the hyperboloid. So we need to understand the group theory of this. Most importantly, what we want to understand is what is a complete basis of states? What is the resolution of the identity in a quantum field theory in the ether space? And so we look at the generators of the group, and they satisfy the Lorentz algebra. And then we can label states if we're interested just, for example, in traceless symmetric representations, which we will be for this talk. Then you can label those with two Casimirs, which are the eigenvalues of some operators that commute with all the others, with all the other generators. And we use this complex label delta. For now, it's just a label for C2. And then we have the quadratic Casimir of SOD, which we call spin. It's related to the spin. And then if we want to span, or we want to construct the full Hilbert space, since this is also the Euclidean conformal group, we can just do the same construction as in CFT. So we take a state and we define it to be a primary if it's an eigenstate of the dilatation operator, which is some particular combination of these embedding generators, and if it's killed by the special conformal transformations. And then you can build all the Hilbert space of this particular irrep by acting with translations, and these are all the descendants then. Then here comes the important part where unitarity comes into play. You ask for these generators to be realized as Hermitian operators on the Hilbert space. And so this fact, together with the algebra, the commutators, implies the form of what is this inner product. Just literally substitute the definition and then do the commutators, etc. And you say that the Hilbert space is spanned by normalizable test functions where this is the norm, the inner product. And asking for positivity and finiteness of the norm, that's what gives you constraints on what the possible values of this delta are, okay? And this is also the crucial difference with ADS and CFT. Yeah.
You said that you will be interested in traceless symmetric.
Yeah. It's just in all the examples that I'm interested in, these are the only states that appear. But yeah, you might consider also more complicated representation, antisymmetric, etc. Yeah, so it's more general. It's just more for some slides for a presentation.
And if you get constraints on this, constraints are beyond the constraints you get from
No. It's precisely those. I'm just pointing out what is the basic origin of those. So yeah, so why is it different in ADS and CFT? Because in those cases, the Lorentzian spacetime, which is the spacetime with respect to which you ask for unitarity, you have to choose a notion of time, right? And then that's a different group. It's SOD, the universal cover of that. And then the embedding space has a different signature. And so the generators, the reality of the generators in terms of the conformal algebra are different, you see. In ADS, P dagger is K, for example, in the Sitter, P dagger is minus P. So that's why in ADS and CFT, you get these very simple constraints, right? Delta has to be real and beyond a certain value. And instead in the Sitter, we see that we get more complicated stuff. And for now, I will focus on 2 dimensions, and then I will talk about higher. But yeah, in 2D, this is the picture. There are only scalars in 2D, scalar states. And the unitary irreps live on what is called the principal series, or the complementary series, or the discrete series, which is all integer deltas. And they are realized in free theories as these are realized as some massive fields with mass higher than Hubble, and these are some light fields. And these things, there are constructions known of free theories where they're realized, and they're realized as shift symmetric scalars. This would just be like a massless scalar, and this is a scalar that has a symmetry where you send phi to phi plus a linear function of x. So you need more derivatives appearing in the action. And as you go on, you have more and more derivatives, more and more shift symmetry. okay? So then, if we were interested in understanding the resolution of the identity, right, to have a completeness relation, if we know all the representations that can appear, we built the whole Hilbert space, we just integrate over the possible values of this complex label delta, and we integrate over x. In 2D, x is really just a real number. Then, if we look at a scalar two-point function, for example, of any operator, we can insert this resolution of the identity. And the nice thing is that these matrix elements are completely fixed by symmetry up to a number. And so the integral over x, you can carry out universally. You will always land on this function, which I will show later, and a number that, since you get a number in its complex conjugate, it has to be positive. And it's called the spectral density. Okay. So what you land is what is called the Chern-Lemon representation. In 2 dimensions, it has this form. We have a principal series and complementary series, and I will describe why you cannot have discrete series if you're looking at a scalar operator. And now, all of the dynamics, so all the details of the theory and the choice of operator, they're just encoded in these coefficients, which have to be positive by construction. And the support of rho, so which actually, what portion of the principal series and the complementary series actually appears. The interpretation is that those are the states that are created by O when it acts on the vacuum. And the poles. Yes, O can be a complex scalar also. Right, it can also be a real scalar on the principal series. You're saying if it's a complex scalar, it cannot be in the complementary series? I don't think. Yes.
But that is O of x and O bar of.
No, I'm thinking in the bulk right now of the sitter, right? And then there is one.
Oh, you're thinking the bulk.
Yeah, exactly. I don't want to go there because, as I will tell now, it's very tricky to talk about operators on the bulk. Yeah. So yeah, as we were saying, the support of these rows are the states, and the poles of these rows, which are random locations in the complex plane, this is what is related to the late time expansion of the operator O. And G delta is the Green's function of the Laplacian with a mass term that is given in this way in 2 dimensions, it's given in this way. So why is there no discrete series? We showed in this paper that you cannot have discrete series because essentially you cannot solve the Laplacian equation okay. Let's say that we are looking at a scalar operator. Then you try to solve this equation and you find 2 solutions, one that grows at infinity and one that has a branch cut at space-like separation. So there's no physical solution. But if your operator has a certain number of indices, for example, 1 index, then you can have here 1 derivative acting on G on the right. And in that case, that cures this problem of the cuts. So if you have enough indices, for example, we will see the stress tensor later, it can have a discrete series contribution with delta up to 2, okay, up to the number of indices. Basically, so we have, this is the statement, then there is a possible loophole, which is that you have an infinite number of discrete series contributions in which they are so tuned that the cuts somehow get cancelled. So we don't have a rigorous final proof that this cannot happen, but if it happens, it's an extremely fine-tuned case. Okay, so let's see a concrete example just to show things explicitly. And let's consider a free theory of a real scalar, and we consider the operator phi squared, which the 2-point function is given by the Wick contraction, so it's just the square of the free 2-point function. And the spectral density can be computed These people computed it a while ago, and it's a product of gamma functions. And this is a structure that returns every time in free theory. They're always like this. You can look at the support, and the support is only the principal series in this mass range. And then there's a complementary series state that appears if you're in a lighter mass range. And you can see this as an analytic continuation of these gamma functions where some poles cross the integration contour of the principal series, and you need to add them. And then those are the complementary series states. Okay, so if you're, so this is the structure in this case. That's a very, so I was thinking of it when I was preparing these slides, and I don't remember what happens in that exact case. I guess the pole sits on top of the contour in that case. It hasn't crossed yet. Maybe you need to add half its contributions, like you have the line and then there's a half circle. Probably that's what happens. But I wanted to check and I forgot. Yeah. But nothing wilder than that. So how do the poles look on the complex plane? You see, if these are the unitary irreps, most of the poles are away from principal or complementary series. These actually sit on the discrete series. That's true. And when you turn on interactions, the nice thing about this framework of spectral densities, etc., is that you can compute anomalous dimensions of all of them in one go, because it's an analytic function. You just take a generic residue, and you can get how they shift. And these are the kinds of trajectories that they go when you turn on lambda phi to the fourth, for example. So the point I wanted to make is that it's complicated to talk about late time operators because there is no state operator map in the sitter, and then even in a free theory, you have a bunch of behaviors that are completely have nothing to do with the spectrum of the theory. And in the literature, people interpret them more as quasi-normal modes of the horizon.
This result says you don't have representations in the reciprocity.
So it says that this thing has certain poles in the complex plane, right? Free theory. And what I'm saying is when you take the late time limit of this equation, you can see that you can close the contour of integration, and you get a bunch of terms that behave at late times behave like CFT two-point functions. But the scaling dimensions are not related to the spectrum, which is the support of these integrals, but it's related to these poles. So you get a bunch of CFT two-point functions with scaling dimensions at these positions. They are not unitary in the de Sitter sense, nor in the CFT sense. Yeah. So if delta phi is in the principal series, when you do twice, you get off of it because you get D, right? And then you're not anymore on that on the principal series.
I didn't understand the statement.
Yeah.
Are you saying that the late time behavior of that?
No, if you take just phi, I agree. In a free theory, it sits on the principal series.
Or just phi sits in the principal?
Yeah.
So then what is, why can't I take the late time just phi?
Yeah. No, there's no problem with that. It's the spectral density will be essentially a Dirac delta, so it's then the late time limit is the CFT with that scaling dimension. When you will turn on interactions in that case, the anomalous dimensions are in general complex, and so it will go off of the line as soon as you turn on interactions. Yeah. Yes. So in phi cubed, you can compute the one loop two-point function of phi, and the pole shifts. It goes like here. There's a theorem that tells you that they always get positive real parts. So it always goes to the right, and then what you get, is again not a principal series operator.
So how is that consistent?
Because unitarity is a statement about the support of these integrals, right? It's like in ADS, I agree that that's what you would expect, because in ADS, this representation is just a basis, right? So you can write it also in ADS. But in ADS, What is positive is what you get when you close this contour of integration. Those are really the states, the discrete sum that you get. And the coefficients of those, which are the residues on the poles of these functions, have to be positive. But in de Sitter, that's not the case. In de Sitter, this is the natural decomposition, where you're decomposing in the spectrum. These are the coefficients that have to be positive. And the poles are related to the late time behavior, but are not related to unitarity or to the spectrum. Unitarity says nothing about those poles. Yes. Yeah.
So you say 5 and 5.
Yeah.
You're saying that the late time behavior now has delta phenomenon.
Yes.
But if I look at the 2-point function, that's still.
Yeah, it's still.
Function,
Oh, no, now it decomposes into a continuum. The same way also in flat space. When you do perturbation theory, the leading correction, you do the channel element decomposition, is not anymore one irrep, but it has a continuum also. It has a leading behavior that is as if you're correcting the mass, and it's one representation, but it also creates a continuum of states, because it's becoming less and less. Yeah. And in de Sitter as well, you still have this decomposition with positive coefficients, but you don't. It's not anymore a delta function. It becomes immediately a resonance in de Sitter if you want. So it develops immediately a width, and it's not stable in particular. Yeah. Yeah, of course it's suppressed. This behavior is suppressed, but there is an imaginary part that is non-zero. So you will have, even if it's suppressed, it will be not on the line. It will be slightly off. So it will not be, yeah. Okay. Yeah, are there more questions about this part of the story?
Sorry, just to reiterate,
Yeah.
there is no clash with unitarity. Or are you saying that?
Flat space unitarity, what do you mean?
There's no clash with unitarity.
No, there's no clash with unitarity, because usually we think of ADS unitarity, where we say, the boundary expansion is into states. The boundary operators are states in the Hilbert space. So the coefficient of that is positive, and there's a one-to-one map. But in de Sitter, there's no state operator map, so you cannot do this reasoning. Yeah. Okay. Okay. There are no more questions. I go on to application number 1. So let me just talk 1 second about RG flows. So for now in flat space, just to set the stage, we know that in 2 dimensions, if you have a unitary local Lorentz invariant QFT, then it interpolates between 2 conformal field theory. Yeah. Yeah.
So let's say I want to do the wave function.
Mm. Yes.
So that,
no, that's true. In that case, the anomalous dimensions, I think, are real. So it stays in the complementary series. Yes. Mm. Yes.
and that will still have these operators that correspond to single primary operator.
So if they do it on the principal series, then they better see this sort of resonances. I think the thing is, when you do it in ADS, it will be a non-unitary theory, right? The theory in ADS will have a doubling of fields, because you have these 2 boundary behaviors in the Bunch-Davis vacuum, and one of them will have a wrong kinetic sign also. So it's like a very sick theory in ADS that you need to. Then you continue to the seat and you should land to the right answer. But the right answer is what I'm saying here, that the principal series will get an imaginary part also. Okay, so what I was saying is in 2 dimensions, everything is settled because scale invariance implies conformal invariance. So this statement actually is not yet, well, there are counterexamples to this statement in 3 dimensions, for example. There's scale invariant, there's QFTs that have fixed point that are not conformal invariant. So for now, we focus on 2 dimensions. And
in 2D, is it always the case?
In 2D, this is a theorem. You find on Di Francesco the proof that if you have scale invariance, immediately the trace of the stress tensor is 0 as an operator statement. And then you have conformal invariance. And then conformal field theories themselves, they're characterized by the central charge, which is some dimensionless number that measures the entropy density and appears in the 2-point function of the stress tensor. And here I showed the classification of all known, well, actually, it's proven that these are the only unitary CFTs with central charge between 0 and 1 in 2D, right? And these are called the rational CFTs or the minimal models. And then above 1, there's a continuum, and there's an example, which is a Liouville CFT that has, you can tune a parameter and scan over all the values of the central charge. Then quantum field theories are flows between these models. For example, you can see the theory of a free massive scalar as a flow between the free massless boson and the empty theory, or the free massive fermion as a flow between the critical Ising model and the empty theory. And here, actually, last week at the conference, someone pointed out that I should not say empty theory because you can have what are called TQFTs, topological quantum field theories, where you have no dynamics, but the Hilbert space is non-trivial, and there can be strange stuff happening. It can be interesting. It's not completely empty, the theory. So in the 80s, Zamolodchikov proved that for every such flow, there exists a particular function that is monotonic, and that it interpolates between the central charges of the CFT in the UV and the one in the IR. And why is it interesting? It's because this monotonicity is sort of, we take it as a quantitative measure of the fact that there is a loss of information when you coarse grain, when you do the RG flow and you go to large distances, because it counts entropy density, right? And so the question to ask was, what about the sitter? Can we say something similar in the sitter? So let me first review Zamolodchikov's theorem. To be more specific, so he defines a QFT as some CFT deformed by a relevant operator. And he shows that the conservation of the stress tensor and unitarity together, they imply that this particular function monotonically interpolates between the CUV and CIR. So what is this? This is the 2-point function of the trace of the stress tensor integrated against some kernel, and we are in 2D Euclidean space. Basically, you cut out a small circle around the origin of radius 1/λ. And this object is a function of this lambda and of the mass scale in your theory. So here, like for simplicity, I'm considering the case where you have one mass scale. Then it only depends on this ratio. And Zamolodchikov showed that it interpolates between these 2 central charges. Okay. And a few years later, it was phrased in terms of spectral densities, which is how we will connect to the sitter. So these authors here showed that you can write this statement, that the difference of the central charges at the endpoints of the flow can be written as an integral over the spectral density of the trace of the stress tensor over all the masses. And they also showed that the 2-point function of the stress tensor can be written in this way. So these are some differential operators that project on that are in particular conserved. The divergence is 0, and as you can see, there's a massless contribution, of which the coefficient is CIR, and then there is all the massive part. And I wanted to say something else. Yeah, importantly, this thing has precisely by itself the form of the two-point function of a stress tensor in a CFT. Okay, it's also traceless, this part. That's important for later. And a similar approach can be taken in the sitter. So what one can do in the sitter is to start by, you do the group theory. So you start, you have some generic two-index symmetric tensor, and you ask what are the possible spectral densities that can appear when you decompose it into states. And you get a lot of them naively, but then you apply conservation and this condition on the discrete series that I mentioned before, and you can show that the only form that it can take is this. You will have principal series, complementary series with the spectral density of the trace of the stress tensor, and then the only discrete series contribution that can appear is this one, where you have delta equals to 2, and this contribution is traceless, and moreover, it takes, again, precisely the form of the two-point function of a CFT, of the stress tensor in a CFT. And the idea then is that as you take the radius of the characteristic length scale of the sitter to infinity, you should match again with the expressions in flat space from before. So yeah, what I said is, yeah, by symmetry, you can show that this is constrained to take the form of the two-point function of T mu in a CFT. So then, what happens? What happens as you take the flat space limit? You can show that this part here reduces precisely to the continuous part in flat space. This part here reproduces precisely to the massless contribution. And also this one, by matching with the sum rule that I showed before for CUV minus CIR, you can show that the complementary series part always goes to 0. And you can think of it just by noticing that complementary series is an interval between massless and some point that is determined by the Hubble constant. So if you take that to 0, this shrinks to 0. There's no complementary series in this limit. But then what follows immediately just by matching with flat space is that the spectral density on this discrete series state has to become the central charge in the IR because here we had CIR appearing, and because this was a two-way function of a CFT, and this is also, I'm saying, has the same form, because a CFT doesn't care whether you're on the sitter or in flat space, then necessarily you need to have this fact. And then we can think of the opposite limit. What about taking R to 0? So taking R to 0, when you fix the mass scales in the theory, is exactly the same thing as fixing R and taking all the mass scales to 0. And that means that you're probing the part of the two-point function that is sensitive to the UV, because you're below you see you're like such a short scale that all the mass scales, all the particles look massless. And since we are probing the UV CFT, in particular, the trace of the stress tensor is 0 as an operator statement, which means that since the trace of the stress tensor appears here, these two things have to be 0. This doesn't care about R, again, because it's a CFT two-point function. And it has to match with what? With what we have on the left-hand side, which is the limit of this two-point function in the UV, which becomes the CFT two-point function with CUV appearing in front. And so this tells you that as R goes to 0, this function has to become, has to extract the central charge of the UV CFT. Okay. So this is a toy proof. Of course, it's more complicated than this if you actually look at the details.
Can I ask something? So
yeah.
I was a bit confused about this statement that when you look at R going to 0 limit, it's because if you're looking at R going to 0, you're looking at very highly curved.
Yes.
functions, right? So in some sense, you're not looking at like flat space.
It's not the flat space limit, definitely. Yeah.
Yeah.
Well, but the fact is, it depends on how what things you keep fixed as you do this limit. And here you're also taking the points to be coincident. Wait, I always get confused here. 1 second.
Because I think the statement was that here you're looking at some very points very close together, and so in some sense there's like a flat limit kind of thing. But that's what you said.
Yeah, but in some sense that also becomes, but not in the sense that you're taking the space to be flat, but you're considering points. So you're considering the UV, and the UV is insensitive to the curvature. But there's an order of limits, and if you start to think about it that way, I get confused. I need to look at the formulas to solve it. But the way that I see it is just this: that all these observables are functions of, they're dimensionless, and so they're functions of products of M and R. And so taking R2, you can just don't think about taking R to 0, fix R, and you think about putting all the mass scales to 0. That means that you're probing the part of the theory that is high in the UV. Or if you have these observables as function of these masses, yeah, you're probing.
Okay, fine. So then you're basically saying that there is nothing on the principal series.
Yes, in this limit, what remains, in particular in the two-point function of the stress tensor, it becomes a CFT two-point function. So the only thing that can remain, you could have said from the beginning, had to be this part that already looks like the CFT two-point function.
But then there should be a contribution from the complementary series, right? Because
why?
Because in some sense now you have like a much larger span of the complementary series.
Right. But
which is the opposite of what happened in the previous.
But the problem is that here I'm not saying that there's no complementary series states. I'm saying as you look at the stress tensor, the trace becomes 0. And this was what, these two things are the spectral densities of the trace. And since that's 0 as an operator statement, this part goes to 0. But I agree that there might be some other observables that is sensitive to the complementary series.
So can you just say what the punchline is? You looked at the 2-point function of the stress tensor.
Yes.
Right. And can you just tell me how are you defining the stress tensor?
It's just the variational derivative of the action with respect to the metric.
So you can think of it in particular
and then it's conserved by no, I'm really thinking of QFT in the Sitter space, and so there's an action that is just integrated over all of the Sitter. Bunch-Davies boundary conditions, yeah. But yeah, so you're saying in the path integral,
you put some boundary conditions that you get a wave function.
No, I'm not thinking of the wave function. I'm thinking of how to generate, like the correlators in the theory, the in correlators, if you want. They're just the path integral of these operators against e to the is. And the boundary conditions on the field is just that at minus infinity, or that you are, that you start from the Euclidean vacuum, from the Bunch-Davies vacuum. But that's for the wave function, right? If you just compute correlation functions, yes, but
that's the same as computing the wave function.
Yeah, but I'm not thinking of the wave function here.
I think of the stress tensor as being the stress tensor of dual CFT with the wave function. And if I write the wave function,
yeah.
I think of the terms that might
I don't think so, because I think this is really the bulk stress tensor. It's like, Yeah, in ADS, you can have, if you're doing QFT in the bulk, you have a stress tensor in the bulk. Yeah.
So it's not the daytime,
No.
but just the bulk.
Yes, 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 yes. Yes.
You're saying I have
Yes, yes. Yes, precisely. So, so the claim is that then if you look at the spectrum of this stress tensor in the bulk, and you do that decomposition, there is one term that single-handedly, that is this function that is, in some sense, counting the degrees of freedom. I mean, we know at the endpoints it gives the two central charges. In between, there is no univocal definition of this sort of stuff, even in flat space. Moreover, I didn't prove monotonicity all along, but I can show through an equation like this that you can write down. You can see that the right-hand side is manifestly positive. These things have to be positive, and these are squares. So, so it will always be smaller than CUV. So in particular, you can show then CUV greater than CIR, which is the main thing from homological theorem. And another point is that it's inherently different from the homological C function, because you would think, oh, maybe I take the flat space limit of this and I retrieve the homological C function. No, you just get CIR. So it's like it's an orthogonal direction. So if you think more a big picture, we're saying quantum field theory has one more constraint. There is the homological C function, but if you place the quantum field theory on a sphere or on the zeta space, you have also this other constraint in another direction, that is the radius of the sphere.
Let's say I take the limit R goes to infinity.
Yes.
That's like taking a flat space.
Yes.
So then I have the stress tensor at 2 points. That stress tensor at 2 points is not necessarily a CFT step. Further RG. Get the CFT.
Yes.
How do you do that further RG?
No, the limit, I'm taking it by also going, I'm taking R to infinity, and the points are becoming closer and closer also.
You're taking R to infinity points and get closer to the y that give you the U.
Yeah.
Pretty sure the R goes to infinity. So now,
Yeah. So let me think 1 second. The geometric picture is always confusing me. Yeah. So the particular way in which I'm taking R to infinity, you can really show explicitly these things, and you can also check them. The geometric picture right now, I'm getting confused. But from the equations, you see that in this limit,
points are also scaling of infinity or something.
yeah, so the distance between the 2 points goes to 0 in this limit. This I know for sure. Yeah. No, yeah, I understand what you're saying. Sorry. No, in fact, we're not getting the CFT. We're not in the IR here. You see, in flat space, we get to flat space. We still have massive contributions. This is not 0. But the point is that if I match with the formula in flat space, where you have, at any point in the RG flow, you have the massive contributions, and you have this thing where CIR appears in front. So I'm just matching the coefficient. So you're right. You're not getting to the IR of the theory. You're getting, I'm just matching this coefficient. Yeah. But you get, there's still something. Yeah. Yeah, I'm just matching this expression in that limit with this expression. And you see, and I'm saying the blue part matches the blue part. The red part just goes to 0. And the orange part, this is already equal to this because they're CFT 2-point function. I'm saying it has the form of a CFT 2-point function, so it doesn't care of the radius. And the only way that it can happen is that you get this coefficient. Yeah.
I want to ask what's the it's not so easy to just extract this part, right?
I'm saying.
How do you separate the zero?
Great. No, those are, if you want, those are, it's just a prescription where you say, because the spectral densities somehow have like, sometimes have a delta function contribution at 0 and a continuum that starts later, okay? So that's cleanly separable. Some other times it's not the case, but you can, so it's just a matter of convention, let's say, of how you separate these integrals. Are you doing it really all the way to 0? Are you keeping delta function contributions or not? This is like you're starting from an epsilon. And so, yeah. And this is the really m equals 0 part.
There is a mass gap in the
No, I'm not assuming this. I don't think so. In fact, if there was a mass gap, then CIR would be just 0. All right. Okay, so one concrete example is to study. Yeah. The last equation is just one of, there are many sum rules that you can derive, and this is one sum rule that you can write down. And the nice thing is that it shows that this is manifestly positive, and the left-hand side then has to be positive. Yeah, I'm saying the only physical part here is really CIR, right? In between, okay, it has an interpretation, is the states.
CIR is not like a central chart.
Yes, it's the central chart of the IR CFT.
You're saying you take out
yeah, and this is telling you that that difference that it has to be smaller than the one in the UV. So one check is, for example, to look at the free massive fermion, which can be seen as a field parametrization of Ising field theory, where m is the how much away from critical temperature you're going. And you can compute the trace of the stress tensor in this theorem is just given by this composite operator. And you can compute the two-point function with the big contractions. And in particular, here I use this. These basically are related to the two-point function of the fermion, and I found it in a very nice form written in this paper for the sitter. And yeah, exactly. And there is another sum rule, there are multiple. This one makes me retrieve this difference from a specific integral of the two-point function, where you have to integrate around the discontinuity at time-like separation.
This free theory is a massive problem.
Yes.
So the flat space limit of this, as you say, is CIR should be 0.
Exactly.
And you find that?
Yes.
Yeah.
So let me just, let me plot what I found. In both cases, I also tried the free massive boson. And you get precisely what you expect, that this spectral density with this specific factor in front goes from 1 to 0 for the free massive boson flow. And for the free massive fermion, it goes from 1/2 to 0. So, and this is a numerical plot, and this instead, you can really extract the analytic function, which is nice. Okay, so I think this, I wanted to mention then last month, some important developments are that Gonzalo Torroba and Nicola Abate, they found monotonic functions in 2, 3, and 4 dimensions. But the difference is that their monotonic functions are related to relative entanglement entropy. So you basically, you fix a region of the sitter, and you ask what is the entanglement entropy in that region in the UV CFT versus in the QFT during the flow, and they show that this function is monotonic in the size of the region. And then it interpolates between CUV, and it doesn't reach CIR because when you're, if you think about it in Euclidean signature, there's a maximal size that the entanglement region can have, so you never truly reach the IR. in this way. And in particular, in 2D, under some limit, they show a relation with the C function, with the spectral density that I found. And yeah, so for me, one interesting open question is whether this group theory approach can be also applied to 3 and 4 dimensions to find C functions in terms of local observables again, instead of entanglement entropy. This is an open question. Okay. So yeah, this concludes the part of 2D. How much time do we have still? Okay. Great. I'm not reading that correctly, yes.
We have 1.5 hours.
1.5. Oh, great. Okay. So if there are no more questions, I move to the next topic.
Sorry, can you go back?
This relation, basically, yeah, it's funny. If you take their function of this size of this region, and you go to the maximal size that you can take, you get in that point, you get one of the C functions that I found. Yeah, and then from then on, but my flow is different, right? My flow, I'm changing the radius of the zeta really. So it's just funny that you find the same function, given that these are completely arbitrary along the flow. There's no independent definition of them, right? At the endpoints, you have the central charge. Along the flow, it's arbitrary. There's an infinite set of C functions if you want, just by small deformations. It's really funny that they find the same function at some point with a completely different approach. Yeah.
So, in some sense, and maybe I'm wrong, but when you get rate time things, or rather, yeah, long distance or rate time things, you are in some sense looking at this argument to zero. So, is that
in what sense are you saying? Because you're going to the light cone in embedding space?
You're looking at long distance and long time.
But R20 is the UV, right? Then that would be the short distance.
Yeah, this is the part of my confusion. But then I that see in general I would say like okay things which depend on very large distances and large times in cosmology will be affected by the cosmology. And at short times and short distances, cosmological constant will be that.
Yeah.
So so in some sense, when you take the limit where the cosmological constant is complete, that should correspond to rate time.
I see what you.
Yeah, this is R going to 0.
Right. Yeah, it's like H to infinity.
In some sense, all the scales that you're looking at
yeah, it's really about the skin.
okay, I mean, yeah, that will depend on that.
Yeah.
But then,
At some point in the time, the 0-point function looks like one like the delta is not to the 4. And there's some scaling with 2 points, you take points. Right?
Okay. So I will go to 4 dimensions now, which is maybe a bit more relevant for the real world. And yeah, I will talk about this strange phenomenon. Yeah.
Do you expect
The what?
he said that
Ah. In what sense do you mean unique?
he said
Ah. No. There are. So in this paper, I also found there's also another C function that is independent of this. So there's just many functions that do this job of interpolating. This is I find it nice because it's group theory. It's just the composition in irreps, and this delta equal 2 irrep somehow.
I'm just taking like errors like
Yes. And you can show at least that this other one I found was always had to be smaller than this or something. So and in flat space also people have found multiple C functions in 2D. And I think there's even a proof that there's an infinite family of them. Yeah. So the interesting part is more the endpoints, and in this case, the fact that this one is fixed by group theory, which is not the case in flat space. Okay. So 4D. Yeah, so there's this interesting phenomenon that was known already in the 80s from group theory, that if you take 2 states in the principal series, and you do the tensor product and you decompose into irreps, you find photons. And this suggests the possibility that you can have some sort of bound states where the 2 particles are pointing, one in the future light and one in the past, which is possible because in the future you don't have positive Hamiltonian, such that the linear combination of the momenta is known. So that something that is made of massive stuff looks like it's a massless photon from afar. And so we were very curious about this, and we've been trying to understand how this relates to the spectral decomposition. And we found something interesting. So first, yeah, let me review what are the unitary irreps in 4D. If you focus on spin 1, then you have the principal series. The complementary series now is shrunk. It's not from 0 to D, but from 1 to 2. And there is only one irrep in this discrete series, or that has many names, exceptional series or whatever. It's the photon. And for spin 2, you get the graviton, but also you get something weird that is called the partially massless graviton, which has a number of degrees of freedom that is in between. It basically has the helicities plus minus 2 and plus minus 1, and it doesn't have the 0 helicity. And instead, the graviton has 5 states, and this has only 4.
This photon is sitting in delta.
Yeah. In 4 dimensions, yes. As delta equals to 1. Yeah. It's 1 or 2. And instead the graviton is 0 or 3. What do you mean? Because if you're interested in the late time behavior, then sure, because actually spin matters. So the power, in the end, this is a constant at late time. So this really survives, and people hope to see this in the measure in the CMB, right? Yeah, and this is the one that decays. Yeah. But as long as you do everything in the bulk, then there's always, every quantity you compute is symmetric. Okay, so how we attacked this problem was to think of operators that have the same symmetries as the field strength. Okay, so it's 2 indices and it's antisymmetric.
When you say looking for the photon, why don't we?
Well, because that we know that it's a photon, it's a free theory. But what I'm saying is, we think that photons are there in theories where there's no gauge field.
You mean that here the OPs?
Yeah, or in this case, in the spectral density, in the spectral decomposition. Then the question is, okay, let me get there exactly, because it is a non-trivial question. What does it mean to look for a photon? I agree. So for now, we're asking the question. I think, okay, it was vibrating. we're asking the question of do the photons appear in the spectral decomposition of massive operators? So we did just a symmetry argument. We do the full decomposition, and we find that what can appear is the principal series, complementary series, and the photon in general for a generic two-index tensor that is antisymmetric. And you always have two densities here and here. You can show by group theory essentially that you can have two different representations. And so, yeah.
If you just take a scalar, then you don't expect to get an antisymmetric.
No, well, actually, in a massive scalar theory, you can build, maybe if you have only one scalar, you cannot, but if you have two scalars, then you can build a composite operator with derivatives. In fact, we looked at that. And by symmetry, this term here is forced to be, by the way, the two-point function of the field strength in free Maxwell theory, okay? Whatever QFT you have, whatever strong interaction, anything, this term here has to look like free Maxwell theory by symmetry, just kinematically. And all the dynamics are encoded in this as these other spectral densities. Okay, so what did we find? Is that there are many massive theories actually that create states in the photon irrep. For example, you take two massive vectors and you build this composite operator, you see that this thing creates photons. Also, you take one massive scalar and one massive vector. I didn't put here the example, but also two massless scalars with those derivatives. And any antisymmetric primary, so you put a CFT in the bulk of the sitter and you look at the decomposition of a antisymmetric primary, it contains a photon. And in all of these cases, if you take this function, you take the flat space limit, you always have zero. So in flat space, this does not happen. And so we were happy, and we were like, oh, wow. So it means that maybe photons can be composite or emergent, etc. But you have to ask another question, which is, yeah, what do you mean by there is a photon? So the state, if you want, yeah, the Fock space is being excited somehow in these theories. The state of the photon is populated, but if you take any of those two-point functions of these operators I mentioned, and you look at the large distance behavior, it does not look like a photon, because there is always, in these cases, a conspiracy between this term, which behaves as a photon at large distances, and these terms, where you always have, in the late time limit, as I said, you have to pick up the poles, right? And there's always a pole that cancels precisely this term here. So these are not, in these free theories, these operators do not behave as photons, but yeah, and so this tells you somehow that also this Wigner's classification, or this approach where you say, the particle is the unitary irrep. So if that unitary irrep appears, then there's that particle. It's kind of, you have to take it with a grain of salt in the sitter, because here you have photon states, but they don't behave as photons.
What is the new element here as opposed to having so you could get like photon.
Yes, but this will always be zero. If you try to do this construction in flat space, this term here always ends up being zero by mass conservation, if you want also. Yeah, energy conservation. You cannot have two massive operators acting on the vacuum creating something that is massless. There will always be a mass gap in these integrals over the mass. If you write the same thing, literally, if you take the flat space limit, you get Heaviside step functions that start from the sum of the masses of the fields.
Flat space QFT, then this would happen.
Yeah, so yes, so right. I thought that this was really completely novel, but someone at the conference also pointed out that in flat space, there are some examples where you get theories that don't have a mass gap, where you have emergent photons. You don't have a gauge field, you have something else that...
Just a conformal field. Just take a CFT,
yeah.
take some scalar operator.
I think in that case, it doesn't work, because that we checked, and the flat space limit.
Free massless scalar. Take free massless.
Yes, and then what operator? Yeah.
And maybe, as you said, you can start some.
So what we checked is for one antisymmetric operator, there is a primary. The two-point function is then fixed by symmetry, and we checked, and there's no photon in flat space. But you're saying, yeah, take two scalars with derivative, two CFT primaries. You act with derivatives and you antisymmetrize. Yeah, that we haven't checked. Yeah.
So you're saying this is
Actually, we did check that because no, we did check that because we did the example of two massless scalars in the sitter. So, and we took the flat space limit, and it was also vanishing the photon density. So I know that there are some examples where this works. I don't know the details, and it looks like you need to cook it up. Like you need to really fine tune stuff. Yeah. So in these free theories, seems that there's no photons. But now the question is, what happens if you couple these things that sort of that have this photon in the spectral density to real photons? So you consider Maxwell's theory with some Proca Lagrangian that gives with two massive vectors, and then you couple them in this way. And this is work in progress. We're trying to see what happens. But by speculating, you might think that some wild stuff starts happening, like you start to generate a mass without breaking gauge invariance, the photon, or there's some mixing, right? Because there's this sort of linear term between this and the state of the photon that is created by these two, and whether the late time behavior of the photon gets modified. And then another thing that started just as a thing that, oh yeah, of course should happen, is that since in the sitter everything can decay into everything else, also light stuff into heavy stuff, we thought it's obvious that also the photon decays into heavy stuff, and that then this would enhance this decay. And this is how then we started going down the rabbit hole of trying to define what it means for stuff to decay in the sitter, which is the last part of my talk, if we're not too late. We can also, yeah. Okay. First, if there are more questions on this part. Okay, so the last few slides about decays. Yeah, the big picture here is that in an interacting quantum field theory, every particle in the sitter is virtual. There are no stable particles because there's no mass gap, in the sense that everything can talk to everything else. There's no conservation of energy, and so as soon as you have interactions, nothing is stable. And also the motivation is that, yeah, this is the production of particles from the vacuum, for example, is the most important feature of QFT cosmology. Okay. No, I guess no, I'm not saying that. I guess that's a good definition. I'm saying that I will give a definition of stability, and which is that whether if you have a single particle, one particle state, whether the survival probability of this one particle state stays constant or it goes to zero. But you're right. I think the bottom line is that what you're saying is that what you should think of fields and not of particle states in the sitter. Yeah. So yeah, so you have these light to heavy decays that are now allowed, also just vacuum to particles decay. And yeah, we wanted to just compute, we were saying, we're going to just compute the decay rate of the photon in QED, but then something more surprising stuff we found that we got confused by. So the setup and the method that we're using is called the Wigner-Weisskopf method, which appeared in a lot of papers by this professor from Pittsburgh, that some were noticed, cited by Weinberg also, but some others were not, and I think they're quite interesting. And then there's also some interesting paper by Higuchi, Maroff, and Morrison, and Polyakov about the stability of the sitter. And I think this goes in that direction. And there's something interesting that is not yet fully understood, I think. So for simplicity, let's start from a theory of three scalars that are weakly interacting with this interaction Hamiltonian. And we think of the interaction as being turned on and then turned off. And we think of a state that starts as being just a one particle state of the phi 0 scalar. And then the interactions at leading order only couple this state with the two particle state of phi 1, phi 2. And then with Schrodinger's equation in the interaction picture, you can write down some differential equation for these coefficients, okay, that couple them in terms of the matrix elements of the interaction Hamiltonian, which you can just compute. There are some integrals of mode functions, if you want, of these fields. And so when you solve these equations, you get something like this. You get the rate, so the derivative of this coefficient with respect to itself, with respect to time and then divided by itself, is given by the real part of this particular integral. And the nice thing is that, again, you can use spectral densities. You can rewrite this both in flat space and in the zeta in this way as an integral over the unitary irreps, and where this part is some kernel that depends on time that you can compute. Okay, so how does this kernel look like? As time passes, if you are in flat space or you are on the principal series in the zeta, then the kernel essentially squeezes on the mass of the mother particle. So here, in principle, you have an integral over all the irreps, but in the end, this becomes a delta function of delta 0, where delta 0 is the mother particle. And so it becomes essentially a rate that depends only on the spectral density evaluated at the irrep of the mother particle. And this is then the difference between flat space and the zeta, as long as you're in the principal series. The only difference is that the spectral density in flat space has support that is cut by a step function like this. And so but if the mother is heavier than the daughters, then in flat space you get a rate that is fully independent of time. And you get that also, the same is true in the zeta, but you see, if you are doing it in this conformal time, then you get this factor. But if you do it in cosmological time, which is the one in which the matrix looks like e to the 2ht in front of the spatial part, then it's really the same result. And so when you plot it for a mother particle heavier than the daughters, the exponent, here I'm plotting the function in the exponent, is just linear, as in flat space. If the mother is lighter than the daughters, you have some oscillations. It's also kind of linear overall. And the interesting thing is, if you take the flat space limit, this thing goes to 0, but the oscillations stay. And that's because for short times, or at any finite time, you can violate energy conservation. So you can have a decay into heavier products also in flat space. But asymptotically, it goes to 0. But now is the weird part. So this was principal series to principal series, but we can consider complementary series to principal series. And then the kernel does not localize anywhere, just centers around mu equals 0, which is the center of the cross of the irreps, is where the mass is of order Hubble. And it starts growing like crazy. So I'm plotting here the exponent, and the exponent in logarithmic scale looks linear. So it's the way that it goes is like e to the minus e to the t. And so this sort of suggests that light stuff, complementary series stuff, decaying into principal series stuff is much more favored than heavy stuff to light stuff if you go across the Hubble scale.
So there's a minus sign. So why is it much more?
No, it's favored for it to decay, is what I mean. Yeah, it decays super fast.
So C1p is a survival problem.
Yes, sorry, yeah. And so if you think of a theory where everything speaks to everything else, then it looks like everything in the complementary series jumps immediately to the principal series.
Can you just explain at the beginning of the talk the series somehow that you like?
That's true.
So
So I'm in the same order in perturbation theory here. So I should be seeing that effect. Yeah, but it's not. This is not a framework of Feynman diagrams, etc. I'm solving Schrodinger's equation at order g squared. So whatever effects Feynman diagrams capture, these also should capture. But I will say a lot of caveats on this. So I'm not fully convinced of this picture as well. But if we, for the moment, believe it, then it looks like, yeah, all complementary series jumps immediately to principal series. And we saw that within the principal series, you're favored to go lighter. And so it seems like there's a special place here where when the mass is equal to 9/4 Hubble squared, that is overall favored. It's the one that decays slowest to the other parts. And so that if you have a theory where everything talks to everything in cosmology, you would expect at the end to land on all the masses being order Hubble. And moreover, the photon is somewhere in this language, in terms of scalars, somewhere here. So we haven't finished the computation, but it looks like the photon also would decay. So which is against the basic intuition, right? So why is this coming out this way, and why should we take it with a huge grain of salt? Is because what we're computing is some overlap of states in the interaction picture, moreover. But what we really measure are correlation functions, right? So what now we want to start to compute are stuff like this. For example, the number counting operator of photons or fermions evolving in time at one loop. This is in QED, for example, or the 2-point function of the field strength. Okay, these are physical observables. It's still interesting to say that, yeah, what this is doing is essentially, so in this picture, in the interaction picture, where states evolve with the interaction Hamiltonian, in a free theory, you would never see the fact that in the sitter we know we have particle production. Here you will get that the state you started with, a single particle state, stays stable because in a free theory. So maybe we're just fooling ourselves by looking at these objects. And what we really should look like is some correlation function. So
let's say you compute the 2-point function.
Yeah.
Separated.
Yeah.
Then what you're really asking is, what is the late time behavior of the 2-point function?
Yeah.
But you already told us that the anomalous dimension gets a real direction.
Yes.
But it doesn't become crazy. So isn't that saying that really it survives because you can measure 2-point function?
Yeah. Yeah.
And somehow the anomalous dimension.
Yeah. So that's, yeah, indeed, I'm confused. I'm confused by the fact that this intuitive quantity here is completely unrelated to, gives a completely different answer than the correlation functions. And there's all these papers of people that studied these and made statements, and maybe they're all wrong. But
I don't know, maybe there's some way to understand it. Yeah, saying the physical thing to measure is the late time.
yeah. 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 I mostly agree. This is more of a provocative point. Yeah. So this is the conclusion. I think, yeah, the main message I want to send is that the spectral decomposition is very useful. You can use it in many different contexts, and there is a connection between group theory and normalization group flows, and that photon states do appear in massive free theories, but it's unclear yet what is the physics and whether that means that you can have emergent photons. So, yeah, I leave you with the open questions.
The statement. The statement that you made about.
Yeah.
Is that about these particular photons that emergent?
No. Right. In general, I just did QED where there's no such, the spectral density of the current does not contain a photon. And even there, when you do these computations, it's a preliminary computation, but you see some behavior like this. So it's just, I think it's the point is that this physics of particles and single particle states is not what is interesting or physical in the sitter. You should really think of correlation functions. I think that's the message. Because maybe what's happening, for example, here for these light fields that decay so fast, is that this is the part due to the interactions, but that the free theory effect of particle production is compensating for it. They're also producing a lot of them from the free theory part, and then overall the correlation function is well behaved.
Essentially, at least from a local point of view, like if you're looking at like the static patch correlation, these are like the state is like thermally populated. So obviously, like something is changed, there's a horizon which is also trying to balance it out.
I guess that's it would be interesting to understand the detailed balance of the particle production versus this decay. More questions?
We know what the lead time limit of dead point function.
At one loop, people will argue whether we know it or not, because actually that's an important point. If you look at these anomalous dimensions that I was mentioning before, they have been computed, and it's weird because think of them as a function of the mass of phi. So you're in phi cubed, then you think of the anomalous dimensions. How do the leading behavior as a late time change? And it's not smooth. There is a divergence at some point as a function of the mass of the field. But if you make it light enough, this anomalous dimension diverges, and then it comes back from minus infinity, and then so no one understands if this analytic continuation is good. So if it's meaningful what you're getting once you reach when you go there, you're really breaking perturbation theory also. And the idea is that you should do degenerate perturbation theory, because what is happening is that one of your late time operators two of your late time operators are mixing. One of the primaries is mixing with one of the descendants. But this is not fully figured out. So the one loop computation, I would trust it on the principal series and for heavy enough complementary series. But beyond that, it's very much an open question. Now at EPFL, Victor and with his student Veronica, they did it in scalar QED and computed the anomalous dimensions for the photon. And what they see is that this constant mode stays fixed due to gauge invariance. So you still get a constant mode that survives at one loop. But this subleading mode also has an anomalous dimension that has a very similar plot where there's a discontinuity at some point, and it diverges, and they're trying to understand how to interpret it, what does it mean, how to treat it properly. But it's these basic things of perturbation theory are not fully figured out.
Let's say you take a principal series.
Mm-hmm.
You said its anomalous dimension becomes constant.
Yes.
So it's not the principal series.
Yeah.
Let's say I take this new complex anomalous dimension, and I think the limit is e goes to infinity. Z to the power this new dimension.
Yes.
This p.
Yes.
Is that limit well defined? Do you get a well defined operator?
What do you mean by well defined?
I mean, does that give you a well defined operator?
I don't think so.
Why not? Isn't that the definition of anomalous dimension?
The way I'm defining it, anomalous dimension, is just that you can resum the logarithms you get in perturbation theory as a shift in the exponent of these terms that you get at late times. But I don't think there is a non-perturbative definition, or I don't think there is a definition for these operators, even in perturbation theory, as operators on the Hilbert space, because you would have something. Imagine that you have a two-point function of this late time operator that is not on the principal series. Then you insert the resolution of the identity in the middle, you get 0 suddenly because because the scaling dimension is outside of the unitary irreps.
No, but I thought you said that you can decompose it unitarily.
Yes.
As a statement about. So in fact,
As long as you keep it slightly in the bulk, or that you keep all the subleading corrections. But
as long as you keep it slightly in the bulk. Sorry, let's say maybe we can. Let's say we write down a
Yeah.
function in the bulk.
Can we raise?
Yeah.
Yeah, right.
So you have some point function that looks like 1 by x1 dot x2 parts twice.
Yeah.
Now this delta has whatever value it has. Might I just take its late time limit? I will get.
This is already, to me, just already looks a boundary to the function. Or you want to start with a
I want to
CFT?
start in the bulk.
You want to start with a CFT in the bulk.
I see.
Otherwise, it's just the 2-point function is like this 2f1, whatever, some hypergeometric. Yeah.
And if I take a limit, won't I just get this boundary 2-point function, a new value of it?
Yes. Yes, I agree. So I will get this, the delta. I will get also the shadow. The shadow, meaning the 2d minus delta. And then I also get a contact term, which is also important. Well, these are all equally important if it's the principal series. Well, if we're starting with the operator in the bulk, then you get all of this. In the complementary series, yes, but in the principal series, no, because they are complex and the real part is the same in these two cases. It's always d over 2, right? You get these two things, but the real part is always d over 2.
What is the operator? Maybe if you look at 5 plus I pi or something.
Okay. That's possible. I can believe that that's possible. Okay.
So you look at
Okay. Yeah. But I'm not sure that this object you're thinking of then has a Chern-Lehmann decomposition. But is it a Hermitian?
It's not Hermitian.
Yeah. So probably it will not. Yeah, then the spectral density doesn't have to be positive, for example.
Well, it has a commission quantity, so I can still look at
okay. But don't I get back this then?
Chi bar might just be the delta function.
Okay.
Might be delta and chi bar.
I see.
You're saying this operator doesn't
what I'm saying is, okay, what I'm saying is the following. If you just keep this, clearly it's some 2-point function that exists.
Yeah.
But if delta is not in the principal series, so this is, I think it's a confusion. I don't think there's any, but if I just take this 2-point function, let's call it O of x1, O of x2. And these look like, really like the states I was using, right? This stuff. So it kind of looks like.
So let's see the stuff. Then is there a problem?
No, then there's no problem. I can do the Chern-Lehmann decomposition. It's all fine. But what I'm saying is that when you try to interpret this as a state like this, but now delta is not in the unitary irreps, it has 0 overlap with all the UIRs.
It's not a Hermitian operator. No. You take the 2-point function which is only that delta. It's not a Hermitian operator.
Right.
So the conjugate of that state is not O of x1. You might, the positivity constraint is on O of x1 to dagger x1.
Right.
That's
I think that it's the full thing that should satisfy the positivity.
So as you said, you can look at different things. You can look at the operator. Also extract from the operator.
Okay. I see. You're saying out of all this stuff, this is what should probably still have a non-zero overlap with the UIRs. That's what you're saying.
That's the one. And these two operators are not commissioned. The one which has this one.
Yeah, yeah.
And so they don't satisfy the same possibility.
Okay.
Then what's the problem?
But right, there is this other element. Sorry, this thing you can only get in a free theory. You will not get this delta function when you do this late time limit in an interacting theory, because you lose this fact that the delta, that these and these get dimensions that are related by d minus the other is not anymore true. So you will have, in an interacting theory, let's say you have delta plus gamma, and here you have d minus delta minus gamma, and gamma is a complex number. So but this is not true. Maybe I mean with a complex conjugate. There's some way in which, I don't remember right now, but that they don't match anymore. The power of this plus the power of this is not anymore d, so you cannot get this sort of terms. But yeah.
This final statement about the
Well, what does it mean that it exists? Yeah, you get these things. Yeah, that's.
Study cosmology correlated.
Yeah, I don't see an issue with that. I just would be very careful with saying, yeah, you just cannot say that it's in the principal series or in the complementary series. It's not an operator that the states that this operator creates when it acts on the vacuum are not in the Hilbert space. But yeah, I think it's a deep confusion that if you keep all the subleading terms, yes. But if you just you construct an operator that just has this two-point function, the sum of these two,
yeah.
I don't know if having the sum of these two is enough. Because I still think if you just, maybe it's enough. Maybe it's enough. Maybe it's enough. I haven't. I think that's it. Yeah. Yes, I think that's it. Yeah, there's also a recent paper by Daniel Bauman and Dan Green where they did this. Yeah, that shows that this thing, that the real part of gamma is always greater than 0, just by even just classically you can say that and then this somehow implies that the sum of the two does not give d anymore, and so you don't have the delta function contribution. No more questions? Thank you.